Thank you. Welcome to Dongguan. Welcome to the 2024 International Workshop on Magnetic Crystallography. And actually, this is a school, so I very much thank you, all of you, and especially lecturers, and also the participants. Our plan to organize this school is back to the last IUCr meeting in Melbourne. And I talked with several colleagues and the members of the commission, IUCr commission. One is the magnetic structure and also neutron scattering. And after that, after coming back to Dongguan, and then I got an email from Maru and also Ishigaki about they strongly support, eager to support us to organize that. So they actually, at that time, especially last year, we are worried about organizing this kind of school in China. It's not so easy because can we gather the good lecturers from overseas or not? We are not certain at that time. But the end of last year, we organized two international conferences. One is November, the other one is December. And many foreigners eager to come, especially Europe. And then actually it was successful. We're soon confident that it is possible. Next worry at the time we had is since solving a structure, magnetic structure here is emerging, so we are not certain how many students, how many participants we can gather. But actually what occurred is over 100 people, participants, eager to join. So we need to ask them to resign to attend this time. So actually we are very happy to welcome and actually welcome you, all of you. And it's a 6-day workshop, it's 6 days school, so it should be very hard. But we're eager to learn each other during this. And then we share all the food and all the talks, and we can enjoy the lecture by the world leading lecturers this time. Okay, let me start my talk, and I'm only talk about the diffractometer overviews, because some of you are not less familiar on this kind of thing, and this is my past 40 years, my experience in actually it is almost the same time, the increase in intensity. Like I got a job after I graduated. I got a job in electron accelerator facility. And then soon after that, I start using proton accelerator, that is sporation. I was very much surprised to know that it is 50 times increase than electron accelerator. And then we have, as you know, we have constructed JPAC facility. It is even more. So finally, we got a 10 to 4 to 10 to 5 increase intensity. So initially, we carefully deal with the neutron because neutron is very valuable, and we need a very big sample. But now we can use only small sample. We can use the isotope, and it can be easy. And we were worried about absorption before, but we can use a small sample. Absorption is less important now. So opportunity is increasing, extending, not only for this kind of technique, but also the users expanding, especially in China. So the talk of my content, this brief history of neutron diffraction and its advantage of neutron, and angle dispersive diffraction, that is using monochromatic neutron, and time of flight using white neutron, and high resolution, high intensity diffractometers in the world. Okay, going back to this is the discovery of neutron and discovery of wave nature of neutron. That is, at that time, just after the Röntgen discovered X-ray, and also X-ray diffraction, and also electron diffraction. At the time, quantum mechanics are emerging. And so the people expect that the neutron have such kind of the wave-particle duality. So 1932, the very famous Chadwick discovered neutron. And soon after that, 4 years later, when Nature of Neutron confirmed initially theory, that is 1936, and same year, an experiment done using a very weak radioactive source, and then that is done in separately, two groups, and then those are published in the same year. And later I will show that the magnetic scattering also proposed in the same year, 1936, but discovered actually experimentally later. Maybe I'll talk about that. This is using a reactor. So compared with the radioactive source, so we can get the good statistic and the quantitative analysis. We can now use the solving the something in the material science with good statistics. So that is essentially necessary. So the door was opened by Ernst Warren in 1944. And then because of a high neutron intensity from reactor, it was shown wave nature of neutron can be used to study structure, material structure. And going back this, and then here, the magnetic structure, using magnetic structure was done by the Schur and Smart in 1949. It's a little bit later, but as most of you know this famous figure, it was done by Schur at all. So this is I'm talking about the advantage of neutron diffraction compared with transmission electron microscope, because the electron microscope can clearly look at this kind of see, and then something. But with neutron, we can get more precise bond length. Actually cannot. And lithium occupancy, this is the atoms, so determine the atomic position precisely and detect as small as 1% of lithium defects. And compared with X-ray diffraction, the neutron can catch the light elements like this lithium or something, and neutron is sensitive to light elements like hydrogen, lithium, or fluorine. So maybe this is the reason many people want to use the neutron, because nowadays the clean energy era. So people more use than compared with before, hydrogen, lithium, or oxygen or something. And this is the scattering power of X-ray. Because the X-ray is scattered by the electrons, and so electromagnetic interaction. So it is proportional, related with the atomic number. So in a sense, X-ray is not sensitive to the light elements. X-ray is hard to distinguish transition metal. But neutron is different. The diameter is proportional to neutron scattering amplitude in femtometer. Minus means the turning over the phase during the scattering. Maybe I will skip about this kind of detail. So neutron is more sensitive to light element, and neutron can distinguish transition metals. So this is the isotope. So scattering length is different between the isotope, and sometimes it is negative or sometimes positive. Neutron can distinguish the isotope. So this is in the case of the hydrogen, lithium, or nickel, and then it depends on the isotope. So value and also sometimes minus or positive. So this is example lithium cobalt O2, and with using a lithium 6 isotope and lithium 7 isotope. So intensity is so different, we can full use of this kind of. So structure factor FHKL depends on HKL. We observe the absolute value of FHKL. So it's anyway, this is obviously different. So I'm talking about the Bragg scattering condition, how to detect the Bragg scattering conditions. So here, so-called angle dispersive method, we use the constant wavelengths and then move the detector. So purpose is to obtain lattice spacing D, move a detector to obtain the angle to satisfy Bragg condition. So this is often used in the reactor facility. And later I'll talk about the energy dispersive variable wavelengths. So this is the Neutron beam from some research reactor in the world. Here, 2-1 is from China, and here the Asia, Opal, Australia, and the GR3 are in Japan, and Korea, Hanaro, Kerry, and Europe, ILL, ELL, and also FRM2, and this is the USA. So since I use this figure often in talking in China, so mostly try to emphasize China. So actually, many reactor facility in Europe. Sorry for skipping many of them. So I talk about this is the energy dispersive method. The purpose is the same: obtain lattice parameter, lattice spacing D, and obtain lambda to satisfy Bragg condition. And lambda is inversely proportional to neutron velocity, actually proportional to time of flight of neutron. So we call that time of flight method, often used in accelerator facilities. I'll talk about that later, now. Okay. So the birth of neutron, time of flight diffraction, the idea was probably Egger stuff from UK, and the first proposed in 1953, and also I found that in 1954, and then some of the symposium report was in the Sacre Symposium on neutron time of flight method in 1961, and there is a paper we can get that in the theoretical description, or what I say, and the intensity gain of time of flight method over the constant wave method. This is this paper in Acta Crystallographica, and then it says the time of flight method utilized wide range of energy spectra. Angle dispersive method utilized a small part of energy spectra using a molecular beta. So there's a which battery?
I don't know why.
I'm Japanese, so some of the Chinese character I can understand, but some of the different. So okay. But the pronunciation is so different, so it is difficult to speak and difficult to understand. Okay, this is the birth of time of flight, the actual experiment by Bura's group, and then how to make a time of flight. I mean, like making a chopper. Initially using a chopper, and then using a Dubuna, like a pulse reactor, actually. So this is also, we can get these papers. Okay, this is initially using a reactor, they can pulse the beam with white neutron, and then
Sorry, we might not have to. I have to use it.
Okay.
Try that now?
Okay. Okay, I can try. あれ? どっか行っちゃった. Okay, so I found the paper searched three different regions did like a time of flight diffraction and using electron line arc. One is in New York, the Runsena University, I found a paper in the Nature. And then, but the group quit to do this kind of job. They did a lot initially, but they didn't continue the experiment. And the Japan, that is Tokyo University, started this kind of work, and they continued, especially neutronics, and tried to connect to the material science. And also similar in UK, Howell, and then Sinclair, and then it was, and the Alan Huard studied a lot, seriously compared to time of flight power diffractometer with angle dispersive one in viewpoint of intensity gain, resolution, achievable small d spacing, etc., which are said to be advantageous time of flight method. But actually, at the time, he understands it's not true, like here, it is written that the time of flight technique may actually be better suited to low and medium resolution instrument if high intensity is required. Since then, short path length and large incident solid angle can be used. But actually, after that, the neutron transportation problem is going to be solved, and was going to be solved, and very advancing later. And then now, many people agree that the high resolution diffractometry is very suited in time of flight. And then Alan's group, and led by him, very angle dispersive neutron diffractometry has been developed, and with using multi-detectors with solar slit, which became the world standard power diffractometer. So there are many Alan Huard type, D2B type diffractometer in the world. I found several, many. And basically the idea is the collimator and monochromatometer, and second collimator, and sample to the third collimator. This is one example of D2B type, and then I think this is Jelly's one. So is utilized only several % of neutron by using a monochromatometer. So the most, even the facility, reactor neutron, so much of neutron we can use, but actually, because of the monochromatometer, only several % of neutron can be used with this, but increase the angle. But how to attain the resolution? Again, further we lose intensity in that sense. So this is the who widths at Hawk maximum diffraction balance. So this is mostly using the angle dispersive 2 theta, the width, just width, half width. And then the delta D over D, that is used in time of flight case. And this is the angle dependence of width at Hawk mass, and then controlling this value of something like incident collimation or more several others, and then we can control this resolution curve. So I'm talking about the proton acceleration. So we call that sun sporation. Protons with energy around 1 JeV bombard heavy metal target. So it's 10 to 30 neutrons per proton are released in entire process. This is very efficient way. So it was now popular to produce high intensity neutron. So it started around this area, so back to the 40, 50 years ago. And now I'll talk later, show the present facility. So here in the yearly increase in the effective intensity, so compared to reactor neutron source itself is constant. Actually, optics is increased, so actually increasing intensity in the reactor. And then this is the source increase in the sporation, or including electron accelerator here, and this is the sporation increasing like this way. And now CSN is going up to the 500 kilowatt, something like that, and increase the number of instruments. And the ESS is going to start soon. We are waiting. So this is the advanced pulse neutron facility. starting from electron liner from different areas in the world, and the USA, Japan, UK, and now this is the sporation, proton acceleration facility sporation, starting in 1980s, and now here, here, red one is in operation. ESS is going to be operated soon. So briefly talk about the time of flight method to obtain the, okay, sorry. This is to just say, want to say, distance time diagram neutron, and this is the time and distance. And then you can easily look at the satellite and roughly 8 kilometer per second speed. And this is the airplane that is 0.3 kilometer per second speed. So most of the neutron we will use is between them. So speed is very slow in a sense. We can easily detect precisely the speed of neutron, like using a Dobroi relationship. So this means neutron wavelengths can be calculated from the time of flight of neutron traveling in the certain distance, that is time of flight. So we can put the detector around there, so we can precisely detect time of flight. And then if we use the 4 ohms of neutron, that they arrive at 100 meters away, and then after 100 milliseconds, if the peak width, pulse width is less than 10 microseconds at 100 milliseconds, and that resolution can be 0.1%, or 0.01%. So with time of flight method, lambda can be determined very precisely. So that is high resolution diffraction. But as was shown, that if the neutron go away, intensity usually decrease. But so transportation of neutron is very important. And this is the two-part diffractometer in CSNS, and then both are located 30 meters. One is looking at the poisoned decoupled modulator. The other was looking at the hydrogen modulator. So it's a different performance. So this is the function, and so this is 4 ohms of neutron arrive at 30 milliseconds later. And this is the EMD, so engineering diffractometer of CSNS, and this is located roughly about 50 meters. So the same 4 ohms of neutron arrive at 50 milliseconds. But because of the CSNS accelerator operating 25 hertz, that means the 40 milliseconds later, next neutron will come up. So very fast neutron can come in. So this was contaminated by, that is we call the frame overlap. So we need to put something to remove that. This is the trend, that is the high resolution power diffractometer of CSNS. The last July started up, and already showed that the highest resolution in the world. And then here frame overlap again, but chopper cut out the neutron. And then we can detect this wavelength of neutron. So this is combined Bragg scattering formula and Dobroi relationship, and we found that this Bragg peak reach after this T here, and the scattering by that. This is the elastic scattering, so this is the time distance diagram. The line is straight because it is elastic scattering. So many Bragg peak is observed at different d-spacing. By those, we can solve the structure. And since as I said, most of the pulse neutron source repeated this kind of pulse, like 25 hertz in CSNS and JPAT, 50 hertz in ICs, and 60 hertz in this SNS. So it's a difference. So something like this repeated this process, and then like that, and then we can, how do I say, overplot? And then we can, like, almost the same time, we can gradually accumulating this process. And this is angle dependence. From this formula, the same black scattering D arrive at a different time depending on L sine theta. So this is the time of flight, and detector angle is different. Small detector, the same black peak arrive early, and then large scattering angle, that is backward bank. Actually, all of these black peak is obtained by backward bank, and then so slightly shifted the time. But we know that this is the same black peak, same D spacing, same HKL. So we can summing up all of them. So so generally, time of flight diffractometer have, especially power diffractometer, have these very, large solid angle detector, and we can simply summing up of them. And then without sacrificing resolution, intensity can get. So that is one of the tricks that compared with the angle dispersive. We call that like a time focusing. So compared with, again, this formula, and then the same D spacing in different detector. If it is so far away, the time of flight of neutron is so different. These are same black peak, but so different. So high angle, the resolution is very high, and D range is limited because it is the same D. But here, low angle, D range is very wide because of the low angle, and the covering large D, but the resolution is low compared to high. But if we compare this peak resolution reactor, angle dispersive one, still it is high, but so we can full use of these features with using a low angle bank. But there is a problem of the angle dispersive, the monochromatic monochromatic wavelengths. So the wavelength dependence term is, we don't have to care. But here, always we have to care about the wavelength dependence of correction. That is weak point of time of flight. So compared with the diffraction pattern with the 2 theta, something like inversely, this was here, this was here. So I just want to inverse. Maybe I will skip. So this is the higher resolution. This is the resolution, and the resolution combination of time resolution and length resolution, and also geometrical angle resolution. So those should be minimized, and we can optimize to reduce. So how to attain this high resolution is modulator development. This is very important, and long flight path, and 2 theta large. So all the high resolution instruments in the world, they generally have a long flight path and then use 2 theta angle large. And the HRPDR ice is going to upgrade it, and then especially increasing the solid angle backward bank. Is that right? And this is the why higher resolution. Low resolution but high intensity, something like, if we know the model, it is okay. And the result of the fitting we can accept. So probably we can accept and correct structure factor. But better resolution one like that. But much higher resolution instrument, we know the detail of the difference. Generally, fitting is not so easy. That means the model is not always perfect. So we can extract reliable structure factor. Sometimes we may discover something we cannot discover with low resolution machine. That is the reason. So this is one of the example compared with ordinary resolution neutron powder diffractometer and high resolution. And this resolution instrument is very high intensity, and this is weaker, but we can both use by depending on the target of the science. So these 3 major highest resolution powder diffractometer at ICES. I started the 40 years old, 30, 40, nearly 40 years ago. And then this is the second one. All of them have a long flight path. And this is the trend here. Maybe you will look at this facility later. And again, this is outside the main building. Okay, maybe I will skip detail or several facilities there. Okay, this is the time of flight powder diffractometer here at CSNS, GPPD, looking at decoupled poison hydrogen moderator, MPI, the same flight path, but different. This is the water moderator that is a room temperature, and this is the 20 K. So it is the maximum, maximum wavelength intensity is different. Maximum intensity of the wavelength is different. So we can, mostly people use like a PDF analysis or total scattering, mostly for the structure analysis and magnetism. And now, as I said, in July, this high resolution machine has started. So this is the selected list of constant wavelength neutron powder diffractometer. This is the recently published with several colleagues. I will put that in my lecture note. So ILL and the FRM2 and the Switzerland, Netherlands, and so on. So many. And this is the Japan and Australia and China, Korea, India. And this is the similarly time of flight powder. Generally, one facility have 4, 5, 6 powder diffractor, depending on the objective, high resolution, high intensity, and generally have a specific, dedicated instrument like high pressure and engineered diffraction in ICES, and also SNS have also SNAP and Barken, that is high pressure dedicated and engineered diffraction. And last, it is a little bit weak, but high intensity, and then often use the SMART and HIPPO, or depending on the topics. And also, JPAC has a high pressure dedicated instrument, and the engineering, both are very highly used. And the CSNS just started high pressure diffractometer, and last year started the engineering diffractometer. Okay, this is the Asian, but I will skip details. So many diffractometer in Asian area. Maybe I will skip that. So this is a summary. And I talked about the brief history of neutron diffraction and its advantage of neutron, and the angle dispersive diffraction, and monochromatic using monochromatic beam, and time of flight, more emphasis on time of flight diffraction because it's not so familiar even now, and also time of flight diffractometer, and I want to emphasize the opportunities have been increasing in China and going to take a role in the worldwide infrastructure. Okay, thank you very much.
So thank you very much for your excellent presentation. So any question, comments? I think especially from the younger scientists question.
So thank you for a wonderful talk. Really, really very interesting, very enlightening. You showed the Chinese spallation neutron source, on a trend graph with effective neutron intensity, compared to other facilities. What's the strategy, the overall strategy with the Chinese spallation neutron source? Is it productivity, number of papers per year? you know, maybe maximum intensity in the world is not like the only important objective.
Maybe you need to. In my opinion, I think was very strong requirement for the individual topics, but also the people working at the CSNS eager to do the new kind of thing, new challenge of the new science open. Initially, have to do the ordinary thing, like ordinary diffraction pattern and all analysis. And then those will be used in their science. I mean, usually neutron particle diffraction is one of the tools generally for the chemists and sometimes physicists. But probably gradually I feel that the people working at CSNS is not satisfied only doing that. And then going to take a role to open the door with news. So that is not only one, but also includes the various kind of instrument. Actually, like using a proton itself, and then like a back-end scattering that is we don't have in Japan, and then they are eager to do the new kind of use.
Different, I think everything about the neutron and also the proton and the muons, anything. If we have the resource. Yeah. So, any other question?
What's the relationship between the moderator and the resolution of the diffractometer?
So it depends on the facility, but the CSNS and also JPAC, MLF, and also SNS also, this at least three kind of modulator. And but strategies are a little bit different. But generally, particle diffractometer wants high resolution. The high resolution is we need high resolution. So pulse should be sharp. So how to make it sharp? That is the trick. So high resolution modulator have to be developed. And the other, the high intensity modulator that is mostly used for inelastic neutron scattering. And between them, high intensity and high resolution, that is other use. And that is, we call that like a decoupled modulator. So, but there is a tail. Like you have used the MPI, they have a little tail, but high intensity. And the other strategy is like JPAC MLF utilize the same temperature, 20 Kelvin. But here, one of them, decoupled modulator, is room temperature. So it is Maxwellian peak is a little bit sharper. So emphasize on shorter wavelengths of neutron. That means utilize for PDF analysis or total scattering. So there are several strategies.
Okay, thank you.